Think of the ocean on a cloudy and windy day. The surface is rough and choppy, with deep troughs and foamy crests, as opposed to smooth rolling waves. Imagine the turbulent ocean being turned upside down and covering the entire sky. It may sound absurd, but that image is a pretty good representation of Asperitas clouds, a very uncommon cloud type that the World Meteorological Organization just identified in 2017. One of the rarest cloud types ever recorded, Asperitas, which translates to rough and uneven, is the first one to be properly added to the WMO's Cloud Atlas in nearly 70 years. Although we have some suggestions, little is known about the formation of Asperitas clouds given how recently they were found. So what distinguishes Asperitas clouds? Why did we not detect them earlier? And can their discovery offer a guide for spotting incredibly uncommon weather occurrences in the future? Join me as we examine stunning high-definition photos of Asperitas clouds, discover what researchers believe may be causing them to appear dramatic, and examine the fascinating ramifications of this uncommon fusion of citizen science and groundbreaking research. Cedar Rapids, Iowa-based amateur photographer Jane Wiggins captured a picture from her office window in 2006 that she described as looking like Armageddon. The Cloud Appreciation Society uploaded the picture on their website after receiving it from her. The image quickly sent shockwaves through the cloud community, who suspected it might be proof of a brand new cloud structure. Using the Cloud Spotter smartphone app, other casual enthusiasts began exchanging their photos and weather alerts with one another so that others might experience it for themselves. This drew the attention of the Royal Meteorological Society, who assembled a case for the World Meteorological Organization using dozens of images gathered by the Cloud Appreciation Society. After much discussion, the WMO announced that Asperitas clouds would be the only type of cloud to have been identified through the use of digital crowdsourcing, marking the first time since 1951 that a completely new type of cloud had been added to the Cloud Atlas. Yet why was this unusual? Who determines what distinguishes a certain cloud form? First, let's go through the basics. Fundamentally, clouds are either liquid droplets or solid particles suspended in a planet's atmosphere. The majority of clouds on Earth are formed of liquid or frozen water, unlike other planets where clouds can be made of methane, ammonia, or even sulfuric acid. Personally, I'm relieved that we don't have many sulfuric acid-based products. When saturated air reaches its dew point, which is the temperature at which water vapor condenses into liquid due to cooling air or increasing saturation from a nearby water source under a specific set of barometric conditions, clouds form. There are 5 main varieties of clouds: stratus, cumulus, stratocumulus, cumulonimbus, and cirrus. Each of these forms is further broken down into various genera according on height. There are a number of accessory clouds, clouds that separate from the parent genus cloud, as well as supplemental features, in addition to these main types. All of them are properly categorized in the WMO Cloud Atlas, which utilizes a nomenclature based on the Linnean system that has been in use since the early 19th century. The WMO is in charge of updating the Cloud Atlas, however updates are incredibly seldom. Cirrus and tortoise was the latest brand new shape to appearing back in 1951. Asperitas clouds have been seen to be stratocumulus or altocumulus, but are currently regarded to be mostly a supplementary feature of stratiform clouds, which are low-elevation layered clouds without vertical development. It's interesting to note that while stratiform clouds often have flat bottoms due to fluctuations in wind and temperature, the tops of these clouds frequently show prominent features. If you've ever gazed out a plane window, you'll undoubtedly be familiar with this since it happens frequently. Asperitas clouds are unusual because of the intricate structures at the bottom. An article aiming to outline the characteristics and factors that lead to the production of Asperitas clouds was released in 2017 by academics from the Cloud Appreciation Society, University of Reading, and McGill University. The rugged, somewhat wave-like cloud base of Asperitas clouds, which lacks the smooth undulating shape of the, perhaps related, undulatus cloud type, is what the authors claim distinguishes them from other types of clouds. The authors speculate that weak oscillatory activity is probably what causes Asperitas clouds because of these semi-wave-like properties. There are several possible reasons for this. One of these is orography, which is the wave-like motion brought on by airflow over mountainous terrain. There may be additional causes, such as atmospheric gravity waves, horizontal wind shear, or convection, which is the transfer of heat or matter between fluid entities. By the way, a gravity wave isn't the same thing as a gravitational wave, in case you're curious. Even while I adore space-time physics, we're not discussing enormous rippling of the fabric of space-time here. When a force disturbs the equilibrium and gravity seeks to restore it, a gravity wave, also known as a wave orbit, is created at the boundary between two fluids. The tides and tsunamis are two well-known instances of gravity waves. Probability is that you have also witnessed how gravity waves affect clouds. These clouds are undulatus. You have probably seen cloud formations like these from the ground before. The view is equally stunning from space. However, Asperitas clouds have a rough surface look that denotes extraordinary instability at the cloud base. These have a chaotic formation, similar to the stormy ocean we previously discussed, as opposed to being smooth and wave-like like the undulatus cloud type we just looked at. Although Kelvin-Helmholtz instability, which results from a velocity shear inside fluids, is frequently present at the top of stratiform clouds, it is more infrequent towards the base of clouds. What could be the reason, then? Although we do not yet know, the authors of the 2017 research mentioned earlier implied that if the cloud is thin enough, this instability may spread downhill from the top of the cloud. Maybe there are various explanations each time. According to the scientist who recorded this time-lapse, gravity waves were passing through an inversion beneath a raised area of instability. You've definitely seen inversions before, where a layer of hotter air traps clouds or even smog. Thunderstorms were predicted, but because to the inversion, they were forced to draw their inflow air from above the inversion rather than from close to the surface. The lift produced by the gravity waves as they passed through the inversion was sufficient to produce a powerful updraft that moved in time with the peak of the gravity wave. The wave's amplitude was augmented by the updraft's improved lift, which also intensified the Asperitas cloud's visual impact. Whatever the mechanism, the rough, choppy appearance seems to be caused by this internal instability disrupting the modest oscillatory activity at the base. So, when you think about it, the chaotic forces that scientists believe are driving instability in an Asperitas cloud aren't all that dissimilar from the winds and currents that cause the ocean to be choppy on a stormy day. Complex fluid dynamics are at work in both instances, leading to uncannily comparable properties. While nature rarely repeats itself, it frequently rhymes. This concludes our introduction to one of the newest and least well-known cloud kinds in history. If you're interested in this, you might want to keep an eye on the sky and take pictures of anything you find fascinating. Who thought we'd still be learning about new kinds of clouds? What else might there be that we are unaware of? And who knows, you might contribute to the subsequent scientific advance. Isn't it interesting what actually occurs in our immediate environment that we may take for granted? Alright everyone, here's where the video ends. Thanks for watching and don't forget to like, share and subscribe.